A little bit bigger than normal. There's still people trickling in. I know. Everyone's got to hide in the back. Right?
They want to be fit at. That's a very good place.
If you want to learn more, get your ass up.
That's why I like being on the board. I get to be up here with the mic.
Yeah. Is Chris McCord here tonight? Have you seen Chris?
I know he moved. So he just like was a week before he did.
I got him a bunch of servers at Rackspace to teach Phoenix or to test Phoenix.
Thank you. Yeah.
No, thank you guys. My God. I've been dying to get Elixir in on like every goddamn project that I do. You know.
If I want a really badass machine to test things with flow, should I just be here? I just need one really badass. Like,
take whatever you want, man.
What is the maximum amount of cores?
Off the top of my head, probably 30. Just off the top of my head, I don't know.
I need to do benchmarks to say that it's going to scale linearly.
Yeah.
As much more work. I think it will. I need that.
We got data centers even, dude. If you want to test in between, whatever.
No, right now it's single machine. This is the best conversation.
Oh, hit me up. I'll get you whatever you need, man.
Yeah, that would be awesome.
For sure, yeah. Yeah. What's that?
Don't move. Also, we have the podium mic, and we also have a wireless mic that clips onto your shirt, and we have.
I want the wireless. I want the. If it's good, I want the.
What do I have on my head? Send that to me. That's a new avatar. Yeah, that's totally an avatar.
Yeah, we got you the wireless mic. I don't knot it up the entire way doing it. Not like that, so some people do, and it gets really worrisome. All right, so I'm going to turn it on for just a second. I muted you. Your mute button's on top right here. All right. You want to go mic check?
Yeah.
One more.
Yeah, we can do that. Hello.
Okay. Yeah, you're live right now, so I unmuted you. So, hold on, let me, audio, hold on, you're muted.
I'm muted. You want me to turn it off?
Give it one more. I got you right here.
Hello?
Okay. You. All right, you're muted, good.
What's up, Captain? Really? Oh my God, we're on the street, man.
José, hey,
I just want to say hello. I have to leave very soon.
All right.
But I'm looking forward to seeing a small portion. Thank you so much for
coming
along this journey. Shout out for movies here. It's up to you. Just a thought.
All right, friends, let's go ahead and get this thing started. Thank you, thank you. Just a normal few quick announcements. I have so many more of you than usual. This is fantastic. I finally have a proper look. So just our few normal quick announcements. One, you'll notice there's a URL here, register.columbusrb.com. Please go there, register yourself. Somebody at the end of the talk will win themselves a JetBrains IDE license if there are at least 30 people. And I'm bad with numbers, but I'm pretty sure we have 30 people out there. The Wi-Fi and password are up on screen. If you can't see them, we're going to go down soon. Just a few quick things. The television at the back is mirroring the display. So if you're having trouble seeing, just find yourself a position back there. There are sandwiches, but I have no idea how many are left. It is a minimum of two, or a limit of 2 per person, a maximum of 2 per person. So please don't take more than that, otherwise people will go hungry. There's beer and soda fountains in the back. You are all, of course, very welcome. Hold on. That's me. So tonight, I'm sorry to say we only have one speaker, so I hope tonight's meeting goes well. Thank you for your fitting glass, I appreciate that. So real quick before we begin, we'd like to thank, everybody here for showing up tonight. Thank you for making this night special. We'd like to thank the board of the Columbus Ruby Brigade for doing this. That includes myself, Mr. Matt Darby, Mr. Benjamin Winkler, wherever he may be. I have bad eyes, so this is Rachel Slavey. It's Tracy Kirby still. So she's here, she's not here. And Tracy Root. Yay, Tracy. Just a reminder, elections are coming up, so if you're interested in that, I expect to see more about that on the mail-in list. And I guess without further ado, let me go ahead and introduce the only speaker we could find for tonight. There it is, thank you. The creator of the Elixir programming language and a member of the Rails core team, José Valim.
Thank you. All right, there are some free spaces here in the front if people in the back are looking for a place to sit. All right, so to get started, all right. So to get started, I want to thank again the meetup for setting it up for today, CoverMyMeds, for giving up the space and bringing me here. And the talk today is about Elixir. It's not going to be a talk like, oh, that's how you use Elixir and so on. It's more about, yes, okay. So I think at the meetup page, we were saying that the talk was going to be about Gen stage and flow. It's not going to be about that. We changed because since we realized, well, it's going to be a talk at the Ruby meetup, I thought it would be better to give a talk that is more focused on how you need to think, how you write software when you're using Elixir. So the title of the talk is Idioms for Building Fault-Tolerant and Distributed Applications. And that's exactly what we're going to learn. It's like how we need to think, what are the new words we need to know when we're writing software in Elixir, and how that changes the way we write software. Before we get started, who here has already used Elixir or wrote some line of, at least one line of code in Elixir? Wow, that's fantastic. Okay, so yeah, so let's get started. So before we go on about idioms per se, I always like to give a little bit of background on why I started Elixir. And one of the reasons why I started Elixir is that, so I was a member of the Rails core team for a while. And some time ago, this was before I joined, this was about 2008, we had Rails 2.2. And one of the big features that was coming Rails 2.2 was thread safety. And the idea here was that the community knew and the Rails core team knew this whole story that today it's very common that, our machines, they're not getting any faster, right? We don't have machines that have 8 gigahertz, right? We started to have machines with more and more cores. So our machines, we have 2 cores, 4 cores. I was just talking to Matt and he said, well, I can easily get you a rack-based machine that has at least 30 cores, right? So given this idea, what we want to do is that, well, if I write a Rails application and then deploy it on a machine with 30 cores, I want my Rails application to use all those 30 cores efficiently. And the way we do that in Ruby, generally the way we leverage concurrency using multiple cores in our machine is that we have threads. And therefore, the whole idea about thread safety is that you're going to get your application and you're going to run it with threads and your application is not going to blow up, right? It's like, it's safe, it's thread safe. But today, when I look back at this, thread safe, it's kind of like a weird word, right? Because safety is really the lowest guarantee that you can give in software, right? Like the guarantee that your software is not going to blow up is the minimum expect. It doesn't say anything about being productive. It doesn't say anything about being performant, being efficient. It just say, well, it's not going to blow up. Try to sell any project with just that guarantee and see how many clients you get. Right, so that was one of the places that we were at. So Rails 2.2 is about thread safety because we knew that is important. And one of the things that make it really hard for me when later I joined the Rails core team and then I was working things related with threads, and I realized that this was kind of a lie actually, because of many reasons. So first, when we are in Ruby, we have many ways of running your Ruby applications. You can use MRI, or you can use JRuby, or you can use Rubinis, and all of them give different guarantees when you're using threads. That made it super really hard to say for sure this is thread safe. The other one is that it's actually hard to prove. How can we say that something is thread safe? So we would write some code, we would thought that we fixed the bug or fixed an issue, and then someone would come with a bug report and say, well, when we just deploy a new version of our application to production, we start to see those errors and then they disappear, and it only happens when there is a high load. And we're like, how can I reproduce that? And then we'd try to guess what was happening. So overall, the whole experience in trying to make Rails thread safe and improving that was very hard, very frustrating. And then I thought, well, if concurrency is becoming more and more important, which is where we are today, okay, we need to do it well. And then I set out to see what other languages, other technologies they were doing to solve those problems. And today, it's even more relevant than it was 8 years ago. So I like to say that in 2016, everything you do in a computer should be using your cores. Like last month, Apple, they announced the Apple II, and your wristwatch has 2 cores now. Okay, so, concurrency using multiple cores is no longer the special case. That's the rule, right? Writing software that runs on a single core, that's the exception today. That's what you should be doing only if you have no other option. And especially, I work at Platform Tech, and we still have a lot of Ruby projects. And sometimes with the team, I see things like, well, this test suite is taking a lot of time, which is a problem that many of you identify with. And isn't it a little bit weird that we say, well, my tests are taking too long, while our machine has like 4 cores, and we are using only 1 core to run the tests? There's a chance you could make our tests 4 times faster by using the resources that are already available in your machine, right? We say, oh, my application is taking long to boot, but when you're booting your application, again, you're using only 1 core, okay? So that's the situation where we were in the past, and it's even more relevant today. So with that problem at hand, well, I want to be more productive. I want to write software more efficient that's going to leverage the hardware that we have today. I set out to look at other technologies, and while I was doing that, I found out about a specific class of programming languages, which is called functional programming languages, that they were really good for writing concurrent software. They all shared some interesting properties that made them well suited for writing concurrent software. And so that was one of the things that I started to explore more and more. And this talk is not about functional programming. I just want to talk about two things regarding functional programming. So in functional programming, the first thing that we do is that we like to make the state explicit, okay? So when you think about object orientation, for example, one of the things that we have with object orientation is that we have objects, and what the objects do is that they encapsulate state, okay? And a lot of the issues we have when we are writing concurrent software is when you have, so imagine that you have an object here and you have two cores, okay, in your machine processing some instructions, and they are trying to change the same object. They are trying to change a state that is inside the object. That can lead to race conditions. Depending on the language you're using, that can lead to segmentation fault. Okay, so functional programming helps avoid this kind of issues because when we don't have objects, usually when we write functional programming code, we try to make the state more explicit. So if it happens that two things are going to try to change the same state, it's easier to find those spots because the state's now is explicit instead of hidden inside objects. And we actually try to minimize state altogether. And the other one is that even with making state explicit, we prefer to do transformations instead of mutations. So in Elixir, if you have an array or a list, and you delete an element of that list, you don't mutate the list, don't change the list, you get a new list without that element. So we're always transforming things instead of mutating, and that solves the problem with having, like two cores trying to change the same place in memory. Well, let's not change the same place in memory, let's transform those things instead of doing mutation. And there is a whole category of functional programming languages, but there was one in particular I fell in love with, which is Erlang, okay? So with the introduction done, we are going to do the following for the rest of the talk. I'm going to talk a little bit about Erlang, okay, and then we're going to go to the interesting part of the talk where we talk about idioms, and then I'm going to talk about Elixir in particular at the end of the talk. So what is Erlang? Okay, so Erlang is both a language and a virtual machine, a runtime, and it was developed by Ericsson, which is a telecommunication company. And what makes Erlang very interesting is that it was designed with a very set of use cases, interesting set of use cases and requirements in mind. So being a telecommunication company, one of the things that they wanted to do with Erlang is to build telephone switches. And what a telephone switch does is that it's able to connect person A to talk with person B. But, if you're building a telephone switch, you don't want to be able to connect just one person talking to another person, right? You want to have multiple people talking to each other, right? Multiple connections. You want to be able to handle as many calls as possible. So here you started to see how when they were designing this language, when they were designing this virtual machine, this runtime, they started to think about concurrency. Well, we need to do concurrency really, really well because we want to deploy a switch and have multiple people using that switch, multiple connections, multiple calls. And then they had another use case that they had in mind is that, for example, when you're thinking about the telecommunication infrastructure, you don't have only one telephone switch, right? You have multiple telephone switches throughout the city, throughout the state. And sometimes you want to call someone, but that person is already talking to some other person through another switch. So the switches, they need to be able to exchange information, right? So you can get, all the calls going through the city and so on. That's nice. Today, they have even more interesting challenges because you add mobility. You are on your phone, and then you are in the train or you are in your car, and then you are going around the city. And then as you go around the city, they need to handle your call from one telephone switch to the other. So the switches need to have this ability where they are communicating with each other and exchange information to know how to route someone through or how to route a call. So they added this requirement. Well, whatever we build here, this needs to have this idea of distribution, have this capability of having nodes, suites talking to each other. And there are a bunch of other interesting use cases. For example, I like to make the joke that we don't receive phone calls from our telephone operator saying, hey, we're going to be in maintenance mode from midnight until 1 a.m., so please don't use your phone, right? That doesn't happen. And so Erlang also has this ability of upgrading the code that is running live in production without dropping the calls, because that's not acceptable as well. If you need to upgrade the code that's live in production, it's going to drop all of the current calls. That's not going to work, right? So they had to solve all of those problems. And they did that. And Erlang was used by Ericsson and restricted to telecommunication for a good period of time, until people realized that this use case that we have here with the telephone switches and so on, it's very similar to the web, right? Where you have a server and you want to have as many clients connected as possible, and those clients are going to be browsers, they're going to be embedded devices, they're going to be mobile phones doing synchronization of data. Sometimes you need to talk to internal endpoints. And it was about 10 years ago that people had this realization, and then we started to see more and more companies using it. So Amazon and Facebook, they use Erlang. Ericsson, Motorola, they're a telecommunication company that they are still using Erlang. I don't remember the exact number, but about 50%, for example, of the whole 3G traffic in Europe goes through Erlang switches, will go through switches running Erlang. So those telecommunication companies, they are still using Erlang a lot. And we even have like more, startup like companies like Heroku. So if you ever deploy an application to Heroku, every time you access your application on Heroku, it goes for a routing layer inside Heroku that is running Erlang. Okay, and Riot is a whole database written on top of Erlang. And there's one use case in particular that got a lot of attention some time ago, which is WhatsApp. So one of the reasons they got a lot of attention is because they were acquired by Facebook by 19 billion or something like that. But what is really nice about them is that they are implemented, their infrastructure, a lot of it is written in Erlang, and they would write blog posts, they would go to Erlang events and talk about how they are deploying their system and how they implemented their system. And it has a lot of interesting discussions. So there's this blog post, which at this point is a little bit old, it's from 2012, where they said they got 2 million connections on a single machine. So WhatsApp is a messaging application, right? You install on your phone and you exchange messages with your friends. And at this point today, they have, I think, 1 billion users, and they handle more messages than the whole global SMS system. That's the size they got to today. But back in 2012, they were writing blog posts how they were able to have 2 million connections on a single machine. So they had their cluster running production, and they had to a single machine 2 million devices connected to that machine and have information coming and going, right? I would send a message to someone, and that information would broadcast to whoever I was talking to or to the group I was on, and so on. And when we look at this particular machine when they wrote at the time, right, it's a quite powerful machine. It's an Intel Xeon with 24 cores and 96 gigabytes of RAM. But even with all this power available, they're using only 40% of the CPU and memory. Later in the talk, they said that they were able to get to 3.5 million connections on a single machine. And this is exactly what we want, right? We want to write a software that is going to run efficiently on our machine using all cores. And then when we go and put it into production in a very powerful machine, is going to be able to use all the resources that's available as well, using only one instance of our application, right? Without having to start multiple ones. So, and looking at Erlang was the idea that led eventually to Elixir. Like, I was looking at this and saying, well, I want to write software that's going to run in this environment because it's just fantastic. So that said, we could say, after this introduction about Elixir and about Erlang, we could say that Elixir is a functional programming language, right? But I think it's even more interesting to say that Elixir is a concurrent programming language. But even more interesting than that, I think I'd like to say that Elixir is a distributed programming language. And we are going to see exactly what those mean. Okay, so now is the second part of the talk where actually we're going to talk about the idioms, which is the thing that is in the title and the promise of the talk, okay? All right, so when we write code in Java, Ruby, Python, C, this is our code, right? We write sequential code that is going to execute instructions, usually in the order that we write them. And that's why threads, they are so hard, right? Because they write the sequential code, and then when that code is executed, you have like the threads, they are interleaving that code, and then you need to look at the code and say, well, how the threads are going to interleave and possibly clash with each other. And in Elixir, it's actually not much different. We also write sequential code. We write code that's going to be executed in the order that we have written it. The difference, though, is that we get the sequential code and we put into something very tiny that we call a process. So from now on to the rest of the talk, every time I say process, I do not mean an operating system process. I mean a very cheap, very lightweight thread of execution. Okay? In the WhatsApp case, didn't I say they had 2 million connections? So they had at least 2 million processes. Okay? They are very cheap, very lightweight. We can create many of those, literally millions. Okay? And that's the first words. If you're talking about idioms, right, we are now starting to increase our vocabulary. And the first word that we learn is a process that's very cheap, very lightweight. And we can create many of those. And those processes, they are isolated, which means that because they're isolated, they cannot stump of each other. They're all doing their own thing. They can all be running at the same time. So when we write software in Elixir, you have all those processes that they're all running at the same time because they're isolated. So we start to have this idea of concurrency, right? They can all be doing their own thing. And whenever they need to communicate with each other, because they need to collaborate towards a certain goal, for example, they exchange messages. They send a message, say, hey, this is the information you need, or I can send a message to ask for some information. Hey, can you please send me a message later about this value that you may have? Okay, so we have processes that are isolated, they are all running at the same time, and they are exchanging messages. Okay, cool. So let's imagine that we're writing this code, okay, that we have here, and that is running with all those processes. And let's zoom in, let's like pick 4 processes and try to understand what they're doing. And let's imagine in particular that this is a web application, okay? So, and if it is a web application, you can think that those 4 processes, they are going to have different responsibilities. For example, one of these processes is responsible to talk to the database. So every time you need to talk to the database, you're going to go and you're going to ask that process, say, hey, can you please send this query to the database? That process is going to talk to the database, get the message back, and so on. You can have a web process, which is the one responsible for every time a browser connects to handle that request, right? That could be the web process. We could have a statistics process that is computing live information about how many users are connected and things of sort. And you could also have a mailer process that is responsible for sending emails, okay? If we break those responsibilities into processes, okay, and they are isolated, we can start to see a distinction between them. And now when we go back, for example, if we are going back to Ruby code, what could actually happen in your application is something very weird, which is a bug while trying to send an email, okay, could bring our whole system down. And now that we've put things apart like this, that sounds very weird, because why sending an email could bring the thing that talks to the database down, or it could be bringing the thing that is accepting web requests down, right? It's really weird when we think about it. And the only reason we don't see it happening in our actual application is because every time Rails calls your code, or every time the web server calls the Rails code, we wrap those things in begin rescue, right? We use like, or try catch depending on the language, or begin rescue, which is a very dangerous concept, right? Because, you know, the whole idea of when we're using begin rescue, what we're rescuing is what? Exceptions. Right? And it's weird, like your code is saying, hey, something exceptionally happened, something that you're not expecting happen. And then we're writing code that says, all right, thank you for the information, but just continue doing whatever it's doing, right? So it's a tricky mindset where we're saying, okay, I'm going to rescue exceptions, and that's a kind of a fine thing to do. So in Elixir, we don't do that, right? Because those things are isolated, and we are usually we don't like to say, well, let's rescue, let's catch that error, or let's rescue that exception. We don't do that. What we say is something different. What we say, like, if there's something wrong while sending the email, because that's in a separate process, we are going to let it crash. It's okay. If something is wrong with sending mail, that particular process can blow up, okay? And because it's isolated, it's not going to affect anything else in the system. And what we do is that we have supervisors. So those processes, they belong to different supervision trees. So the mailer is going to belong to a certain supervisor, the web and stats is going to belong to another supervisor, and then the B is going to belong to another supervisor. And the whole goal of the supervisor is just to notice when things go wrong and start a new process in its place. So if something is wrong while sending an email, that process is going to blow up. It's going to have a supervisor that's going to say, oh, there was something wrong when you're sending an email. Let me start a new one. And then it's going to start a new process that's now going to send the emails again. And that's a very powerful idea. Why? So let's just think a little bit. Like, sometimes I'm using my computer and then something weird starts to happen. Like there is a flickering in the corner of my screen. There's a tweet. Something weird is happening. And then it doesn't disappear. And then I restart my machine, and the problem is gone. Right? Sometimes the problem never comes back. I use the computer for 3 more years and I never see that problem again. Right? And the reason why restarting fixes it, it's because the manufacturers, the ones that produce our computer, they really test the boot instructions. And then when we restart it, we go back to the working state, to the initial state that's very well tested. Right? There's one thing that your computer manufacturer should not screw up, which is the boot instructions, right? Because if you cannot boot, then it's game over. You cannot do anything, right? And then this is the same idea. If something goes wrong with the mailer, I'm going to just restart it. And when I restart it, it goes back to that initial state, which is the one we test, the one that's guaranteed to work, okay? So if we're talking again about vocabulary, we're talking about processes now, and we have a new word, which is a supervisor. And the supervisor is a process in itself that is responsible to supervise, to see what the other processes are doing, and if something goes wrong, we are going to react to that. And we can see here that we have a supervisor, and then sometimes the supervisor, they have supervisors themselves. So it starts to look like a tree of processes that are doing work and being supervised. And when we have this tree of process, we package everything inside something that we call an application. And I understand the talk may be a little, we're starting to get too abstract. So in order to try to drive those points home, I have prepared a couple of live demos so we can go and explore a little bit. So in this live demo, since we're talking about web application, I'm going to use Phoenix. So Phoenix is a web framework that is written in Elixir, and we say, we are usually, most of the web frameworks, they kind of give this false dilemma for us. They say, well, you need to choose between performance or productivity, right? Or you're going to be super productive, but it's not going to be very performant. Or you can choose this very low level tool that is going to be performant, but not going to be super productive. And then we think they're saying, no, you don't have to choose, right? You can have both. You can write productive, reliable, and fast applications. And so you can go check more information about Phoenix. Let me jump to the demo, okay? So, all right. So here I have started this demo application early on. And what I'm going to do is that I'm just going to start Elixir. So similar to Ruby, where we have interactive Ruby, we have this thing called interactive Elixir. And I'm going to start my application. And here I can type any Elixir code, okay? But one of the things that I want to do here is that I'm going to start this application that is called Observer, okay? And that's one of the nice things with Erlang is that they have very obvious names for things, like the supervisor supervises and the observer observes. So if I run this command, observer start, it's going to start this beauty right here that we can see. And this thing can give all the information that we need about our system. So, for example, in this first tab, the first pane we're here right now, we get general system information, like how much memory this thing is using, for how long it's running, how much cores, how much CPUs it can see there on my machine, how much I/O input and output, all kind of things. All right, and we can see, Phoenix doesn't use a lot of memory in general, so this application that we have just boot is using only 30 megabytes. And that's something in general happens for Elixir applications. So we have also a project, and I don't remember if I get time to talk about it at the end of the talk, but we also have a Nervous project that allows you to get a operating system alongside Elixir and your application, like your Phoenix application, in 20 megabytes and deploy to a embedded software and have that boot up in like 2 seconds. So there are a lot of interesting things on that side, but anyway, I'm going on a tangent here. So the first one gives all kinds of system information, right, about this particular Phoenix application that is running. We can also get load charts, but I just started this application, so there are no requests coming, so nothing interesting is going to happen here. We can see memory allocators, so we can see exactly how much memory it's using and exactly where that memory is being used. Is it being to allocate strings? Is it being used to allocate atoms, which is very similar to Ruby symbols? So you can get all this kind of information here and so on. But and there are other things you can do. You can trace the system and so on. But there are 2 particular panes I love to talk about. So the first one is the processes one. So remember that we were saying all of the Elixir code that we write, it runs inside processes, which are those very lightweight, very cheap thread of execution, right? In this pane here, it lists all the processes in the system, okay? And we can actually go around and double click them and try to understand what they're doing. I can double click this one and say, oh, that's this process. It's running this code. It has this particular state. It's associated with those other processes. You can see here in the bottom, you can see how much memory in particular this very lightweight, cheap thing is using and so on, okay? But what is really cool about this is that, so this is a Phoenix application, and one of the things that we did, when Phoenix started, it has one main feature which is called Phoenix channels. And the idea behind Phoenix channels is that, you can use your browser, your phone, connect it to the server and have information coming and going all the time. When the Rails folks, they announced that Action Cable later on, they said one of the projects they looked at was exactly Phoenix channels for some of the ideas behind Action Cable. Okay, so it's very similar to Action Cable in the sense that it's about having an open channel of communication between client and server. And one of the things that we wanted to do for Phoenix is to make sure if we could get the same results as WhatsApp. So WhatsApp, they were able to get 2 million connections, right, on a single machine. And then we're like, well, let's see how far we can go with Phoenix. So we started to benchmark. We deployed a Phoenix application to production. I don't remember exactly the numbers, but it was a very powerful machine. I think it had 40 cores or something like that. And we set up a bunch of clients. We started to send requests. And then the first time we ran those benchmarks, we were able to get only 30,000 clients on a single machine. And they were like, oh, wow, it seems that we have reached the bottleneck. You know how we solved this bottleneck? We connected to that machine that was running production. We started Observer, and then we came here to the Observer, to the process pane, and ordered by message queue. Because those processes, they exchange, when they need to communicate, they exchange messages with each other. So every process has a message queue of messages they need to process. So if you have a bottleneck, it's very likely what is happening is that a bunch of processes, for example, if you have like 40 cores, you can have a bunch of processes that are all sending message to the same process, and that process can simply not keep up with that. So we came here, we ordered by message queue, and we could see that there was indeed a process that had thousands, hundreds of thousands of messages, and it could not keep up. And then we say, look, there's our bottleneck. We double-clicked, we knew exactly which code it was running, and then we solved the bottleneck. And then we did it again, and then there was, I think, then we were able to get to 80,000, and then we did the same thing. We came to the Observer, we ordered by message queue, we found the next bottleneck. And then after 2 or 3 rounds, we were able to have 2 million clients, 2 million clients connected to a single machine in production, reproducing the WhatsApp case, which was really nice, right? So this thing here gives us writing everything in terms of processes, and having a tool like Observer gives us a lot of introspection into the system and trying to understand what our system is doing. For example, if you have a memory leak, what you can do is that you can order the processes by memory and see which process has memory growing with time. And then you, after a couple of times, going to be honest, look, this process is just growing. Let's do something about it. And then you can go and introspect the system. Cool, so that's one of the things, the nice things we can do with Observer and when we are thinking about processes and writing about processes. But the other thing that we're doing is that we're talking about applications. So we have this other pane here that shows what applications is about. And when we write software in Elixir, we don't have a single application. We have multiple applications running side by side. It may be easier for you to think about them as components, right? They are, you don't run a single one. They have multiple applications running side by side. So for example, here, if we go to the Applications tab, we can see many of them. So one of them is Cowboy. Cowboy is the name of the web server that we use. And then the other one, Elixir itself, is an application. And we can see here the Elixir supervision tree, all the processes that are responsible to make Elixir work. Phoenix itself is another application that has its supervision tree, and so on, and so on, and so on. Okay? And this application, this Phoenix application in particular, it's called Demo. And here we can see our own supervision tree, the one that is responsible for our application. Okay? So we can see here that it has a supervisor, right? We can see here that it has a repository. So a repository is how we talk to the database. So if we're writing a web application, one of the things that we usually want to do is talk to the database. And the way talking to the database work in the majority of languages is that you have a pool of processes, right? So when you start an application, you start like 10 connections to the database. And then every time you need to talk to the database, you have this pool of connections. Say, hey, give me one of these connections so I can talk to the database and get information coming and going. So that's very similar to Elixir, and we can see here, it's clear here, it's visual, we can see and explore. And because those are all processes, I can do the same thing, I can try to double click them and see what is happening, each of those connections to the database, but we can do even more interesting stuff, which is the following. So here in this, so just to sum up, we have the repository here, which is the thing that is responsible for abstracting how we talk to the database, and it has a pool of connections that are all connected to the database. And now that we can see this here, we can see the supervision tree and those processes, we can ask, well, what is going to happen to our system if the database, for example, suddenly decides to close one of those connections, okay? Or if there is a bug and that particular connection goes down. What I can do is that I can do a right click here, and then I can come and say, hey, I want to kill this process. So I can send a message to that process, and I can kill that process, which is emulating a failure. What's going to happen if something goes wrong? And what we expect to happen, because we have supervisors, we expect the supervisor to notice that one of the connections to the database went down and start another one automatically in its place. And that's exactly what we see here. We can see now that the ID here at the top, so yeah, I didn't say about this, but those numbers, they are identifiers for the process. So every process we start has an identifier. And we can see that we have those low numbers. And now, because we killed that one, it started a new process with a more recent process identifier. So, the thing just noticed, the supervisor noticed that something went wrong, and started a new connection in its place. Okay, and as we're going to see, that's how we start to have an idea of systems that self-heal. Because it doesn't matter, which programming language you're using. You can be used the most fantastic type system in the world, but bugs are going to happen in production, right? The database is going to disappear for 2 seconds. Unexpected things are going to happen. So our system needs to know how to react to those failures, and it knows how to go back to the working state, to that initial state. And the supervisors, they play a very important role in that. And we can even be more radical. We can say, well, what if there is a bug in the connection pool? Right, and then something goes wrong there, and that whole connection pool process crashes. We can say, okay, let's kill the whole pool and see what's going to happen. And now what we see is that because the pool is gone, everything that pool was managing all those connections, they are now lost. And a new pool was started because the pool process supervised it and started a bunch of connections in its place. Ooh, cool. So, yeah. All right. So we're talking about applications. So just to sum up very quickly, what applications are about. So they provide us this unified package where we group our code and we know how, and applications know how to initialize a particular component and how to configure that. So this is something really nice that is part of the language, which is all the code that you write, it belongs to an application. And if you know how to configure one application, you know how to configure all other applications, right? It's one unified scheme given by the language. But applications give us a huge amount of introspection and monitoring, right? Because I can go to the supervision tree in each of the applications, and I can double click things around and try to understand what each of those things are doing. So it gives us the visibility of the application state, right? Because everything is in processes, and I can go and I can click and I can try to understand. And applications also give us reasoning when things go wrong, right? I can go there and say, well, what is going to happen if something goes wrong here? And I can try to do it. And I can emulate those failures and see how my system is going to react. So if you're talking about idioms, right, we learned a bunch of new words, new interesting words. We're not talking about processes that are very cheap, very lightweight. We are talking about supervisors that are processes themselves, but they have one very specific role, which is to supervise other processes and act when things go wrong. We have applications, which is where we package this whole thing. And we're also talking about message passing, which is how processes communicate. And we got a bunch of interesting properties from this. We got concurrency because the processes, they are isolated, so they can all be running at the same time. We are now talking about failing fast or let it crash. If something goes wrong, it's fine. It's fine for that process to crash because the supervisor is going to act on it. And that's how we get fault-tolerant systems. Systems that know how to self-heal. When something goes wrong, it can go back to a working state. It can, it's like if you self-heal in the sense like if you kill a part of a supervision tree, that part is going to be restarted. It's going to go back to its initial version. But there is one property that I actually talked about at the beginning of the talk, but we haven't explored yet, which is the whole aspect of distributed. Okay, so how all those things allow us to also write distributed systems. Systems where we have different machines, and those machines, they can talk and exchange information with each other. And the reason we can do that, if we go back to our earlier slides where we have all those processes sending messages to each other, the reason why it's very easy to write, not easy, but the reason it's simple to write distributed systems in Elixir is because when we exchange messages, the fact of process talking to each other and doing the message passing, that's actually abstracted by the virtual machine in a way that it doesn't matter if processes that are in the same node or different nodes. So here, for example, if I want to get some processes and run them on a separate node, as long as I have the identifier, I can send messages between machines and everything works transparently. I'm going to do a very another live demo really, really soon. All right, I'll skip this part for now. So that was the second part of the talk, which was everything about the idioms. Okay, how we need to think, what are the abstractions, the vocabulary you need to learn to write software in Elixir. And in a way, you don't necessarily need to, I know that this talk is going about those very idioms, those very basic abstractions, but in a way, on the other side of things, we have like frameworks like Phoenix that is also abstracting a lot of this work for you, right? So for example, you don't need to necessarily care about how we are doing the connection pooling, but it's very rewarding to know that if you are running a project in production and you need to get that introspection, that thing is going to be available, right? You don't need to worry about the details in particular, but the fact that the whole infrastructure is built on top of that means that when you need it, if we eventually need it, everything is there, okay? And the thing is, everything I showed so far, it's not only specific to Elixir. All the languages, so, like if we go to the Java virtual machine, we have a bunch of languages that run the Java virtual machine, right? We have Java, we have Scala, we have Clojure, etc., etc. And very similar to the Erlang virtual machine as well. We have many languages. And everything I have said so far, it applies to all the languages in the Erlang virtual machine because it's really a property of the runtime of the virtual machine. There's no way to escape from that. So that said, you may be wondering, okay, so what makes Elixir special compared to all the other languages that we have in this runtime? And that's the third part of the talk I want to explore, okay? And in order to do that, I like to focus on the three goals we have for the language. So the goals are compatibility, extensibility, and productivity. So compatibility is really simple, right? It's basically saying everything I have said so far, okay, all those properties that we have with processes, supervisors, they are going to apply to Elixir. They come from the virtual machine and they're still going to be valid to Elixir. It's valid to the point that you can use Elixir and call Erlang libraries, and you can have Erlang libraries calling Elixir with no performance cost. There is no bridging, there is no calling. So Erlang has been around for 3 decades, and if someone has already solved your problem, you can just use the Erlang library, and there's going to be no cost in doing that. So that's our focus on compatibility. The second goal is extensibility. And I love this quote from Guy Steele. It's one of my favorite talks of all time. It's called Growing a Language. And at the end of the talk, he says this: now we need to go meta. We should now think of a language design as being a pattern for language designs, a tool for making more tools of the same kind. And the idea here is that today the computer science field is so wide that we cannot possibly design a language that is going to work across all the domains. Okay, so we need to write a global language. We need to write a language that we can get it and extend it to the domain we're working on. So let's see some examples. So this, I think, is the first time we see some Elixir code. Okay, so this is how we write a test in Elixir. All of our code in Elixir is defined inside the modules. So here you can see def module, map test. I'm defining a module called map test. And because I'm writing a test, I want to use the functionality that comes with the Xcine test framework. And then I can just say, hey, this is my test. I want to do basic operations. And inside my test, I'm going to assert that 1 + 1 is equal to 2. If we use, for example, something like XUnit in Java or mini-test or test unit in Ruby, this is a no-go, right? You should never do this. You should never say assert something equals something. Instead, you should use things like assert equal. Because if you write your tests like this in those languages, if something goes wrong, it's going to give you a very bad error message, something like expected true and got false. Okay? But in Elixir, we don't care. It's fine to write code like this because assert can actually look at the code. We say that assert is a macro, and as a macro, it can look at the code and say, hey, I can see here that you're trying to compare two numbers. So, you don't need to use one particular API like assert equal to do that. The code knows, the language knows. And then when something goes wrong, when there is an error, you get very good error reports like this one. You have something say, well, so this is the code we're going to our test. I was expecting that calling this thing would return this. And then the error says exactly, well, we're trying to convert the things, but we can see here that one was expecting foo, the other one was expecting bar. So, those things are not equal. We can see another example here in the bottom where we are expecting hello world, but it came hello world with a exclamation mark, and we don't want an exclamation mark. So this is a very particular example where someone got Elixir and extended into the testing domain. Another example that I really like is Ecto. So Ecto is a library to talk to the database in Elixir, and here's an Ecto query. Okay, so we write the query using this Elixir code. So you can say, for every p equals, I want to get all the posts that were posted before now, and the author was me, and I want to order by creating that. Okay, and again, it's the same idea. From is a macro, it can look at your code, and it's going to compile as much as possible this query to SQL during compilation time. So when you have to run things in production, right, when people are actually accessing your application, this is as close to SQL as possible. And we just go and run the query. And it's going to bring you security features, going to protect you against SQL injection attacks and everything we expect. Okay, so this is another example where someone got Elixir and extended to the domain of talk to the database. And we can see examples in Phoenix of people getting Elixir and extending to the domain of writing web applications. So we have a router. I briefly mentioned the Nerves project, which is someone taking Elixir and bringing it to the domain of writing embedded software. Cool, so that's about extensibility, right? It's about really making the language should be growable. We should be able to get it and extend it to the domain, the area we're working on. And the third goal is productivity. And productivity is kind of a tricky goal, right? How can you say that one language is more productive than the other? So one of the things that we did for productivity is to focus a lot on having a very good tooling. Okay, having a very good learning and getting started experience. So one of the things that we do about that is to have first-class documentation. We like to say documentation should be easy to write and easy to read. We have very good tooling. So XUnit, which is a test framework, ships as part of the language. We have IX, which we briefly saw, which is interactive Elixir, is part of the language as well. We have Mix, which is a build tool. So for those who are not familiar with Elixir and are familiar with Ruby, Mix is kind of a mixture of Rake, Bundler, and Ruby Gem. So instead of having multiple tools where each of those solve a different problem, everything is behind one unified API, this unified tool called Mix. And we also have a package manager called Hex. Okay, so let's do another very quick demo and explore a little bit more of those things, okay? So what I'm going to do here is, all right, you could not see, all right. Okay, so what I'm going to do here, so Mix is basically the tool used to do everything, to generate new applications, compile our code, run tasks. So I'm going to do Mix new sample, that's going to create a new application. And now I can go to that application and run something like Mix test, and it's going to go compile my code and run the test for me. Okay, so everything you do, you use Mix. So what we're talking about? So we're talking about first-class documentation. So if I start something like IX, which is interactive Elixir, this is the thing we're using to write. We can write an Elixir code, and remember I said documentation should be easy to write and easy to read. And the easy to read means that documentation should be accessible from anywhere. So if you're here, for example, in the terminal, and you're like, well, I want to know what is available for manipulating strings. I can go and I can access the string module, and then I can hit tab. It's going to show all the functions that are in the string module, and then I can say H. Sorry, let me go back. So H is for help. Okay, so if I say H string module and I can hit tab, it's going to show me all the functions I have available. And I can say, okay, I want to see the help for the del case function. It's going to print, the documentation right here, right? And then we can say, well, it has a documentation with examples. So this whole idea that documentation should really be accessible, right? Or I can get the documentation for the whole string module and see everything that is there to know about strings. So this is just one of the examples of where the documentation is accessible. Documentation is also accessible for our editor. We can generate documentation in EPUB formats, HTML. So this whole idea, should be easy to read. Let's see the part where documentation is also easy to write. Okay, so let me start an editor here. And so this is application that I just generated. I don't think you'll be able, well, let me go. So let's very quickly explore the sidebar here. So we can see here that we have a lib directory that has a sample file. It has a test directory that tells you that's where we're going to write tests exactly for this file that we generate with. It has Mix access. So Mix access configures your project, is where we say which version I'm using and this sort of stuff. And there's also a configuration file where you can configure that particular project and its dependencies if you have any. So that's a very, you're going to have like 10 files max. That's the default structure we generate. Okay? And let's play with this a little bit more. So this is the application we generate. Oh, sorry. This is one of the files that we generate, the sample file. And we can see here that it defines a module as we saw before. So def module samp. And then we say, look, here's the documentation for this module. We just write it inline here. And then we say, look, here's the documentation for this function. So we have a function called hello world, okay? And you write the documentations and you include examples, and that's it. And documentation, it's written in Markdown, which most developers are familiar with. That makes it very accessible. And we can see here that we focus a lot when we're writing documentation, that we focus a lot on examples. And that's because Elixir has a feature called doc tests, which means that if you include examples in your documentation, when you run the tests, we'll actually extract those examples, and we are going to guarantee that the examples are up to date. So imagine, for example, we change the implementation here of hello to return hello. Instead of returning the atom, the symbol world, we are returning world with an exclamation mark at the end. Now, if I run my tests, I'm going to get a failure, okay? Exactly because of this idea that if I have code samples in my documentation, I can actually go and test them, which is really neat. What else is there about document? And it's the same thing. So while I was able to, so when I did hstring, I accessed the documentation for a module in Elixir, but I can also do hsample, which is the module that we have in the application, and that's going to show the documentation for the code we write as well. So that's like, it doesn't matter if it's Elixir, if it's Phoenix, or if it's any other dependency, the documentation is accessible, and you're going to be able to access that. What else? So I talked about tooling. We already saw a test example. We talked about documentation. I'm not going to show package managers because I don't want to rely on the internet. That's usually doesn't go well. But there is a place in your mixxs file where you would go and specify your dependencies. So if you're using Phoenix, you would just come here and say, well, I want to use Phoenix version 1.2, right? And that's where you would put your dependencies. Any ideas from non-Elixir developers of things they could show? Oh, the distribution part. Okay, that's the most exciting part I was forgetting about. Okay, so we saw some examples of, Elixir code and things around. I want to show one last one, which is the whole distribution aspect, right? So remember that we were saying that we can start different Elixir instances on different nodes, and they can talk to each other. Okay, so I will show this happening. So what I'm going to do here is that I'm going to start IX as usual, as we were doing before, okay? But now I'm going to, when I do that, I'm going to give it a name. I'm going to give it a short name, which means this particular instance is going to be available with a name on this machine only, and I'm going to name it full, okay? So I started IX, but now it has a name. And what I'm going to do here is that I'm going to define a module like hello, similar to the one we saw before, world. So I'm defining a module called hello. It's going to have a function named world, and what we want to do inside this function is to print hello world. Okay. So now we define a module and don't care about this gibberish it returns for now. But now that I have defined it, I can call hello.world, and that prints hello world, right? And returns okay, saying, hey, yes, we're able to print that. Cool. Now what I'm going to do is that I'm going to go to another tab, and I'm going to start another IX section, but I'm going to give it the name of bar. We named this one foo, I'm going to call this one bar. And now if I try to call hello.world, it's not going to work because I defined this module only on the other one, okay? But because nodes, I gave them names, I can actually get them to talk to each other. So what I can do is that on bar, I can say, I want to spawn a new process, okay, on the node identified by, I'm going to come and copy it here, on the node identified by foo@macbook2. And what I want this process to do, I want it to execute this code that is in this function. And what I want it to do is that I want it to call hello.world. Okay? So what we're doing is that we're connected to the other node and saying, hey, I want you to start a new process that is going to run this code. And when I do that, now it works. I got hello.world back, and I got the process identifier that identified the process that is running on the other machine. If I wanted, I could save that and send it messages and so on, right? So, it worked. And what is really interesting about this, what is really nice, is that we can see that here we didn't get hello world printed again, we actually got Hello World to print it back on the machine that started the request. And the reason why it works is that when we send the request from this machine, from this instance, it goes to the other instance and say, hey, I wanted to execute this code, but if you need to do any kind of I/O, I want you to send a message back to me so I can bring that to the user. And that's fantastic for debugging live systems, right? Which means that you can connect it to a machine that's running production, you can call some functions, you can execute instructions, and that's going to be printed in your terminal and not on the terminal or whatever that is running the production machine, right? So that's really neat, and that's a very simple example of distribution. In the talk I had, and then you can say, okay, why do I care about this, right? We had this slide that I skipped, which is, so what is really nice about Phoenix shares is that, which is the thing that allows multiple files to access the server, is that it relies on this whole distribution aspect to provide distribution by default. So you don't need to use a database, you don't need to use Redis for doing multiple machines deployment in Phoenix. If you have this setup where you have, like, for example, a browser connected to a server, and then other machines connect to another server, if the browser sends a message here, because the machines need to talk to each other, this machine is going to tell the other machine, say, hey, the browser sent a message, so send to all the other clients that you have that this message arrived. And everything just works. Like the machines are able to exchange information, broadcast this information between them. I could go on and on and on. I think I already figured that part out. So that I could be talking for hours. So let me finish this talk. So this is an example of the Elixir documentation. So it goes with that whole story, right? Documentation should be accessible, and we have very accessible, very readable documentation for Elixir, and that's the same documentation you can get for our projects as well. This is another example we saw. Just accessing documentation from the command line. We have. The community is constantly working on tooling for editors. So if you use Emacs, which I expect not going to be many of, it's not going to be a lot of you, but if you use Emacs, we have this tool called Alchemist, and that was the first one in the Elixir community that really tried to bring the A game when it comes to integration between Elixir and editors. And it provides, makes it accessible to compile. You can double-click things and get the expansion, access documentation, everything you expect. And the reason I link to them is because they were really the first. They were the pioneers. Samuel Tonini did a really great job on that. And after that, all the other editors, they were like, oh, I want that too. And then the community started to grow. And usually all editors, the big editors, they have very good tooling for that. Here is our package manager. It started as something for Elixir, but today it grew to the point that it became the package manager for the whole Erlang ecosystem. It's called Hex. You can go and find more information. And then if you want to get started, one of the ways to get started with the language, you can go to our website. We have here at the top, you have a getting started guide. We have actually 3 guides on the website, but one of them is the one that's going to allow you to get started, and it's going to explain the main concepts behind the language, so you can have a quick taste of what Elixir is about. There's also a more advanced guide that's going to explore more in depth all of the idioms that we have explored during the middle of the talk. In the advanced guide in particular, we actually build distributed TCP servers that are routing requests between them. So it's like you're building a to-do list using TCP servers, and it's distributed, which is really cool as a guide, right, to write and being able to do that. I don't think there's any other language that is showing how to do distributed stuff on the guides very early on. So that's really nice, and if that's one of the aspects you want to explore, go ahead. We also have plenty of books, both from getting started books to more advanced. So Programming Elixir was written by Dave Thomas, which is many of us in the Ruby community, we know about him because he's from Pragmatic Programmers. The book that brought Ruby to Western civilization was his Pickaxe Ruby book, and he wrote the Programming Elixir book. So if you're coming from Ruby, for example, it's one of the best introductory talks because he came from the same background, right? He came from Ruby to Elixir.
But we have other, we have other books. For example, the Orion book, which is more of a general introduction to programming, but using Elixir as that introduction. We have Elixir in Action, which is more focused on writing these fault-tolerant and robust applications. It's more an advanced book. If you're interested in the macros that I briefly mentioned, like the assert macro or the actual macro kind of thing that talks to the database, that's a way of doing metaprogramming in Elixir, so there's a more advanced metaprogramming book, and so on. So you can go to the website, click on the learning resources. We have screencasts, podcasts, Elixir School, which is an initiative to bring Elixir tutorials about different tools in different languages. So there are many options out there. And then finally, I just want to say that Elixir was built and designed as platform attack. If you are a Ruby developer, you probably heard of us because of other projects such as Devise and Simpleform, and we have been investing on Elixir for almost 5 years at this point. So we're doing that since the beginning, and it's really rewarding to see the community growing and growing interest and so on. Yeah, that's it. That's the talk about Elixir. Thank you, and should we do questions kind of thing? Yeah, so thank you, and we can have a session of questions and talk a little bit about it, but I'll also stay around, so afterwards. If anybody has questions, I will have a microphone, I'll run that over. Ready.
I was just curious what's coming in 1.4 specifically that Gen Stage might become part of the standard library, or if you had more changes planned coming with it.
Okay, so Elixir right now is version 1.3, and we have version 1.4 should arrive by the end of the year. And I don't think so. So Elixir, we are at the point where there are no very big bangs happening. Like when we got to 1.0, it was like, hey, that's the language that we want the community to build on top of. And there are some ideas that we're exploring on the side, like Gen Stage. And for those who are not familiar, so Gen Stage is a way to build computation pipelines. So imagine, for example, that you have an external queue system where you want to get information and you want to get like events into your system and process them. You can use Gen Stage to do that. One of the talks I gave about Gen Stage in a meetup, we kind of did something very similar to Delay Job or Sidekick using Gen Stage, and it was about like 150 lines of code. So that's the idea, that you can get data from external systems and have a bunch of workers, we call them consumers, working on that. And I'm not sure if it's going to be part of Elixir 1.4. Right now, it's an experimental separate project that you can use today. And to make it part of Elixir 1.4, we need more people from the community trying it out and giving feedback. I already know that there are many people using it in production, and it's working well. But I would like to get a little bit more feedback to be confident that that's the thing. And there are no many big things planned for 1.4 for now, which I think is a feature, right? It means that we are getting stable. Cool. More questions? Let's take like 2 more, and then we can have a break. Yeah. So is there? Yeah, there at the back.
I have that eye, but your hands are.
Yeah.
So there's people coming to Elixir. So what sorts of, bad habits you can see coming from Ruby or other languages?
Okay, so that's a good question. So people coming to Elixir, what kind of bad habits can we see? So one of the things that is important, and it's kind of what we highlighted in this talk, right? Like Elixir requires you to think about software differently, and we have a couple of properties that we like to have in our software. So for example, one bad idiom, one thing that you cannot do, and we mentioned in the talk, is to rescue exceptions, right? Usually we save exceptions for exceptional cases. So if you're raising an exception, it's because you are not meant to rescue that thing, okay? So that's one of the things that need adapting to. One of the things that we wrote a blog post, and you can check on the Platform Attack blog, which is called Writing Assertive Code with Elixir. So one of the things that we also like to do in Elixir is to write code that is very assertive on formats. So for example, one of the things I would not do, especially coming from Ruby, so in Ruby, we have something like, so Rails, for example, add the blank method to all of the objects, right? And then you can call it and not really care if it's new, if it's an empty string, if it's an array, or what else. And that's something for us that we would, for example, not do. We like to be more confident about our code in the sense of like, what is this thing I am receiving here? And I want to be assertive that that thing has a particular property or has a particular shape. And there are a lot of conveniences in the language to allow us to write code exactly like that. That's going to assert that something has a certain shape or a certain property. So that's some other example. Does anyone can think any other examples that say, oh, people should not do that? Yeah, so another one is using struct like objects. So structs in Elixir, they're like key value things. It has fields and it can add values to the thing, to the fields. But Elixir doesn't have the idea of objects. And then people, they can come with the impression that, oh, this struct is going to be like my objects things because it has this property where you have fields and those fields can have values. But that's usually not the way we would solve things. We like to, it's not an object-oriented language. We like to keep data apart from behavior, and that's something that's important that we need to leverage. And not doing that, would not be idiomatic Elixir code. Yeah, there are probably other examples, but on the top of my head, those could be 3. But it's something that as you write code, you get more confident about leveraging those properties that you have in the language, like writing assertive code, not rely on exceptions, and as you use and Elixir standard libraries, for example, those libraries we're talking about, it follows those things very closely. So as you get familiar with the code, you start to build this intuition as well. Like, hey, that's how they do things. Okay, that makes sense now. Cool. One more. We had one question in the back. Yeah. And yeah, we'll take yours and then have a break.
So I really like the concept of self-healing and restarting processes. But I guess I'm trying to wrap my head around the idea of are there tools or frameworks built into Erlang or Elixir where when things go wrong, you can know about it and be logged or reported on, and it's restarted and things go back to the state of realizing the bug.
Yeah, great question. So the thing is, well, the supervisor thinks it's a great thing, right? But what is going to happen when things go wrong? So by default, when something goes wrong, everything's logged. So let's do here. I'm going to start a task, and a task is a process that executes something in particular, okay? And let's make it raise. And you can see here that it reported the logger came here at the bottom. So this is the error you get because you're connected, and here is the error that you can see logged. So this is Elixir logger acting, saying there was this error happening at this time, and it was the process identified by this that was started from this other process, and this is exactly what went wrong, and the code it was executing was this one that was calling those arguments, and all those things, they go to the Elixir logger, and you can add multiple backends to the Elixir logger. So for example, if you want to connect to logger and get this information and publish this to an external service, we'll be able to do that by just adding a backend. I believe there is integration for many of those external systems already, so you just need to plug something, and then when the process crashes, when something goes wrong, you're going to get those reports. In general, so what is really interesting about this is that if we go back to what I was saying, that everything is built with Erlang, and they were built to write those. They're built for running those huge systems, like telecommunication systems. So all the things you can think about, like from observer to tracing how an event affects the whole distributed system, to logging, to monitoring, to statistics, like all those capabilities, they are there in the virtual machine, and we can leverage those things. So it's really amazing all the things we can do. The thing that the Elixir community is doing is getting that thing and put it, put it behind a nice service or something that is integrated. But the capability, it's there in the VM, and we can explore it in many different ways. If you want to explore it by logging to an external third-party system that you pay for, sure, you can do that. But you can also do all other kinds of stuff. It's just insane the amount of information you can get from the live running system and work with that. It's really fantastic. All right, one last question. Sure. Here. Yeah.
What can you send in messages between processes, and in particular, what are first-class objects in Elixir? Can you send modules and higher-level things like that from process to process?
Yeah, so what can you send between processes? You can send any Elixir term. So one of the things that we're going to learn about Elixir is that we have a predefined set of data types, and those are the data types in the language, and you cannot add your own. And one of the reasons is exactly that. We need to know everything that the language has, so we can send that information between nodes, and you can send everything between nodes. You can send process identifier themselves, so I can get the process identifier, send to the other process, or send to another node, and have the information going. I can send strings, I can send anything really. One of the things, let me see if I have this here still. Okay, so the last demo, I promise. So when I wrote this code, okay, with the hello module, right? I defined this module here, right? Def hello, def road, and remember it returned this gibberish here, okay? So when I send a module between processes or between nodes, I'm only sending the module reference. Like, what is that module name? I did not necessarily send the module content. But this thing here that we can see, this gibberish here with numbers, this is a binary. This is the byte code of the module, okay? So what I'm going to do is that, so this is the node that defined hello world, right? So if I call hello world here, it's going to print hello world. And this is the other node. Did I shut it down? I shut it down. Let me start again. And this is the node where you cannot actually call hello world because it was defined elsewhere. But we can do something really neat, which is, because when we define the module, I got the byte code, I can get this byte code, send it to the other node, and say, hey, load this thing and have this thing available in memory. So that's what we're going to do. So I'm going to do is that I'm going to write view1, and that's going to get me exactly that thing that I returned. And we can see here that it's returning a tuple with 4 elements, which is the module, okay? We don't care about that. So I don't care about the first element. I don't care about the second element. I care about the third element, which is the byte code, which is the binary. And I don't care about the fourth element, which is this tuple we have right here. So I'm going to get the first value that we had in the session, which is all this thing, and I want to extract the binary out. So now I have the binary here, okay? So there are many ways I can communicate between nodes. One of them was using node spawn. Let me try to do that and see if it works. So I'm going to call, I don't remember all right, so I'm going to call, I want to execute some code in bar now, okay? So I'm going to get, I want to spawn a process in bar, and what I want this thing to do is to load the binary, and I don't remember the argument, so I'm going to guess, and we'll see how it works. So we want to load code in that other node, and the arguments are the name of the module, I think, the name of the file that defined the module, which I think we're going to say, oh, it was defined in IX, and the binary itself. Okay, so let's run this. Okay, let's see. So after we execute that, now let's see if hello world is going to be available, and it is. Right, so we got the bytecode from one place. Right, so you can do, you can exchange all kinds of things that you want. You can even get the bytecode, get it from one machine, send it to the other, load, and have that module available. And now that thing here is permanently available. Yeah, so to answer your question, the short answer is anything, really. All right. So thank you so much for your time. I'll still be around if you have more questions.
Fantastic talk. Thank you. Ladies and gentlemen, that was José Valim. I think just now was the first incident of completely spontaneous applause during a talk we've had in quite some time. So, thank you to our speaker. Once again, I apologize for having no more speakers tonight, but I don't know how we can have anybody follow this. That said, the winner of tonight's drawing for a JetBrains IDE is Rob Stevenson. Are you around still?
There's Rob.
Stand up, give your hand.
Yeah.
Congratulations.
Yay, Rob!
And with that concludes our evening tonight. Once again, our speaker roster is a little bit light this evening, but man, if that wasn't just an amazing talk. So feel free to stick around and socialize. You're welcome to as much beer and soda in the back as you like. I have no idea how many sandwiches there are left, but if there's one or two of them, you're welcome to fight over them. And thank you all for a wonderful evening.